Welcome back to our final day of this IEC 2023 here in the beautiful city of Baku. It has been a tradition to open the last day of the IEC with a session dedicated to late-breaking news. And what would be more fitting than the outstanding, exciting mission and success of Chandrayaan-3. And therefore, I welcome you to this session, Chandrayaan-3 Lunar South Pole Landing Endeavour, the initial results in exploring lunar South Pole. It is of great gratitude we have towards ISRO that they chose the IEC 2023 as the exclusive venue to unveil the preliminary results of this historic mission to the lunar South Pole. And it is now my great pleasure to call on stage Dr. Anurup, Dr. Gaurisankar, Dr. Kumar, and Dr. Joseph. Please give them a round of applause.
Very good morning to all. And thanks, Dr. Christian, for the nice introduction. And thanks for giving us this opportunity to deliver the talk on Chandrayaan-3 as the late-breaking news to the ISA community. So, this is how we have structured our presentation. What I am going to do here is, I will be giving a brief introduction on our lunar exploration program, the evolution leading to Chandrayaan-3. And Mr. Anurup here will be talking about the Chandrayaan-3 configuration, how it got evolved, and something about the tests and the simulations done. Dr. Anil Kumar will be talking about the mission itself up to the lunar landing. And finally, Dr. Gaurisankar will give the insights into the scientific instruments and some of the results from the experiments. So, to start with, this is how we evolved our lunar exploration program. We had Chandrayaan-1 back in 2008. It was basically an orbiter mission. There was no lander in it. Chandrayaan-2 was done in 2019. It was a full-fledged mission with the orbiter, the lander, and the rover. And the orbiter is still functioning very well in the lunar orbit, but the landing part, as we all know, did not succeed. And now we have Chandrayaan-3 this year, 2023. So, coming back to Chandrayaan-1, this was our first mission. And as we can see here, the Chandrayaan-1, the satellite mass was around 1,400 kg. Because at that time, we didn't have a bigger launcher. So we had to use our PSLV, the Polar Satellite Launch Vehicle, to launch the Chandrayaan-1. So the satellite mass, we had to limit it to around 1.4 ton. But then we had a suite of scientific payloads from India as well as from multiple countries, from US, from European countries. And the outcome is we have more than 180 scientific publications. And of course, the detection of water molecule on the moon by the M3 payload by NASA was one of the greatest achievements at that time. So we launched Chandrayaan-2 in 2019, and that was our first landing attempt. Now we can see the mass is around 3,900 kg, almost 4 ton, because at that time we had a more powerful launcher, the LV-M3. So we were able to carry much bigger payload. And we are going to hear more about the launcher in the next presentation. So Chandrayaan-2 was a full-fledged mission. We had the orbiter, we had the lander, and the rover. And the orbiter is still functioning very well, giving many scientific results. And what is shown here is some of the images taken by the terrain mapping camera on board the orbiter. Again, some of the images taken by the Chandrayaan-2 orbiter on the moon. So on the left side here, what we are seeing here is a SAR image taken by the orbiter, and alongside it, we have the optical image also. So what we are trying to bring out here is the subsurface features on the moon's surface are captured very well by the SAR image. And the right side, what we see is the high-resolution image taken by the OHRC. That is the optical high-resolution camera. That is what is shown on the right side. And a zoomed view also is shown on the far right. So what is important here is we have used these images of this OHRC for Chandrayaan-3 landing also, for finally defining the landing site. And another important point is the orbiter served as a communication link between the Chandrayaan, during the Chandrayaan-3, between the communication link between the Chandrayaan-3 lander and the Earth. So it acted as a redundant link in addition to the direct main link from the lander to the Earth. So, as we all know, the landing attempt during the Chandrayaan-2, we could not succeed. So what is shown here is the landing profile. We have in the vertical axis, we have the altitude, and on the horizontal axis, we have the distance, that is the downrange. And also the time also is plotted here. And what we can see here is the initial phase, the phase 1, as well as the phase 2, that is the rough braking phase. In both phases, up to altitude of around 7.4 kilometer and the range of 8.3 kilometer, the performance was okay and it performed well. But during the third phase, which is called the camera coasting phase, there was larger thrust dispersion, larger thrust in the lower throttling range because of certain logic issues in the thrust control algorithm. So what happened is in the final phase, that is the fine braking phase, it resulted in higher velocities and loss of altitude, which the software algorithm couldn't handle the dispersions. So it resulted in crash landing. So what we have done in Chandrayaan-3 is we have tried to introduce better thrust control system, and it was implemented. And we made some changes in Chandrayaan-3, both in the software algorithms and as well as robustness in hardware, so as to improve the overall ruggedness or the robustness to handle the wider dispersions. So in a nutshell, what we are trying to tell is we try to maximally utilize the heritage from the previous missions, Chandrayaan-1 and 2. We built in more robustness, more number of ground tests and simulation, which are closer to the actual flight was done, and also better features were introduced, including features for on-orbit testing and corrections if required for arriving at the final configuration of Chandrayaan-3. So Chandrayaan-3 is our return to the moon, and the objectives was first to demonstrate the safe landing, followed by the rover deployment, the movement of the rover on the moon surface, and then conduct the in-situ scientific experiments. So this slide gives in a nutshell of how we are going about it. The launch was on 14th July from Sriharikota, India, and then we had 5 earth burns around the Earth, followed by the injection to the lunar transfer trajectory. So we had the lunar orbit insertion on 5th of August, the lander separation from the propulsion module on 17th, and finally the landing on the moon on 23rd August. And it was supported by multiple countries, ground stations across the globe, from India as well as our partner countries. So thank you, and Andrew will be taking over from here.
A very good morning to all of you. My previous speaker, Mr. Victor Joseph, had covered how the Chandrayaan program of India evolved and how we implemented the lessons learned towards the success that we are seeing in Chandrayaan-3. So I'll be taking you through what were the mission elements on the Chandrayaan-3 up to the launch phase. So these are the various mission elements. Obviously, we have the launcher, which injected the Chandrayaan-3 to a highly elliptical orbit of 170 into 36,500 kilometers. And the Chandrayaan-3 mass was just slightly more than what the spacecraft mass on the Chandrayaan-2. The composite spacecraft consisted of the propulsion module, which was mainly the function of which was to take it from the Earth orbit to the lunar orbit, followed by the lander module and also including the rover module. As you can see from the slide, that the mission objectives were, of course, a safe and soft landing, and the rover and in-situ scientific experiments. And there were 3 scientific experiments on the lander, 2 on the rover, and propulsion module on 1 number. In the successive slides, you will see that how Chandrayaan-2, which was launched earlier, played a very complementary role in ensuring the success of Chandrayaan-3. So what were the improvements in Chandrayaan-3? My previous speaker had introduced the root cause of the issues that were faced in Chandrayaan-2. So basically, we had to improve upon the propulsion, the propellant feed system, and also improve upon the guidance and control algorithm in order to provide a highly reliable, safe, and soft landings. In the process, we also improved the robustness of the lander legs and included full redundancy for the sensors so that we get, there are no points of single point failure, and the enhanced the simulations and ground tests so that we rigorously test until you are fully satisfied that we have actually tested as you fly. So these were the special tests and simulations. There are a lot of, it was really a painful process for us to actually devise new test beds, special tests, including all the conditions and distortions that can happen during the landing phase. So mainly we had 3 tests. The integrated cold test where only the sensor, all the integrated sensors were tested on a helicopter at various altitudes. Then the hot test with the actual thrusters firing, and several profiles of the lander leg drop test. So I'll be just showing you a video of the various tests. Just sit back and watch. So this is, yeah. Yeah. No, we need to play the video.
ICT was conceived to validate integrated performance of all sensors, NGC hardware and software algorithms. An MI-17 helicopter was used for ICT to test sensors for its entire operation regime, including hovering at 1.3 kilometers, 800 meters, and 150 meters, and global altitude tests up to 10 meters altitude, which couldn't be done in LSPT during Chandrayaan-2 due to limitation of aircraft operating range. The tests were done at Chitradurga, wherein a special test site with simulated lunar craters were created to simulate landing site. 25 hours of flight time was used to conduct several tests with different combinations of sensors. The outcome of ICT provided several takeaways to fine-tune sensor parameters. The successful conduct of integrated cold test has provided greater confidence in the performance of all the onboard sensors and associated navigation algorithms. Integrated performance of all sensors and NGC was evaluated under engine firing condition for the first time in IHT. A set of dry run tests, static tests, closed loop tests, deboost and compact mission profile tests were conducted as part of IHT. Hovering and vertical descent of lander is demonstrated in ISRO, and this has enabled successful validation of closed-loop performance of all sensors, propulsion system, navigation, guidance, and control algorithms. Performance of optical cameras and 3D output of LHDAC is also validated in these tests. The test was conducted at SDSE Shah, which provided a benign weather condition in comparison to Chandrayaan-2 NAPT test site. Simulated lunar craters were created for IHT-2 for LHDAC performance evaluation. The successful conduct of IHT has provided great confidence in the overall system. Improved design of lander legs was validated through a series of drop tests starting from component level to integrated simulator and fuel structure level, with different touchdown conditions such as on hard surface, soft surface, flat bed, 12-degree slope edge, simulating different combinations of vertical velocity and horizontal velocity. A new facility was realized at QRSC to have a 11-meter by 7-meter test bed with flat and inclined drop surface. Lunar simulated soils were used as contact media for drop tests.
Yeah, so as you can see, the amount of tests that went into the mission is just enormous, and multiple levels of reviews are held to actually go through the outcome of these results, and all the whole process and configuration was further refined, and finally we have the results to show. So now I just go through the individual mission elements. Of course, the lander, which we named as Vikram after the founder of ISRO, Vikram Sarabhai. Yes, the lander was had some instruments, the communication with the deep space networks. Then there was also a communication with the earlier launched Chandrayaan-2 orbiter. Next we had the Pragyan, the rover, with a mass of 26 kg with 2 payloads. And the main communication was with the lander, from where the lander would further communicate to Earth. And finally, we come to the launcher. So, as you know, the LVM-3 is a newly operational launch vehicle, and the first operational flight was used for the previous Chandrayaan mission. Subsequently, there were 2 other commercial missions for OneWeb, and the 4th mission was earmarked for this prestigious Chandrayaan-3 mission. And having the heritage of these missions, and the launcher did do its job fantastically to inject the satellite to the precise orbit from which it could be taken towards the moon, towards safe and soft landing. Further, I would call upon Dr. Anil Kumar to take you through the post-launch operations and the further mission operations until we achieve the landing. Thank you.
A very good morning to all. And as you know, our Chandrayaan-3 landing is one of the greatest achievements India has in the recent past. and it has attracted a record number of viewers in the YouTube as well. And in fact, YouTube authorities have congratulated ISRO for that purpose, and about 4 billion live at that time. So much enthusiasm was there in the Chandrayaan-3 landing event across the globe. And now I will directly go to mission aspects. Now, considering the mission, especially there are three important phases in the mission. One is Earth-centric phase, second is lunar transfer phase, and the third is the moon-centric, lunar-centric phase. In Earth-centric phase, first one is pre-launch phase. Pre-launch phase, as all of us know, that satellite is mated with the launch vehicle, and all types of simulations are carried out, checkouts are carried out, interfacing the ground segments together with the satellite. All network simulations are done. A full rehearsal as on launch day, it is carried out 2 days, and made sure that everything goes well. And also, for liftoff clearance of the LBM-3 vehicle, so that it can be, inject the satellite into a proper orbit safely. Collision avoidance analysis are carried out, and based on the collision avoidance analysis, the liftoff time was shifted by 4 seconds, so that there was no collision threats for the orbiter for the Chandrayaan-3 in its injected orbit. And also, all ground software, they were tested well before the launch as part of the pre-launch simulations. And launch and ascent phase, as we know that liftoff is taken place very smoothly, and it was a textbook launch. And during the ascent phase, all the parameters were monitored, telemetered to the various ground stations owned by India as well as other foreign agencies. And all analysis, all health parameters were online checked, and all the systems were perfectly working. All the stages were nominally working, and it injected into a precise orbit of the Chandrayaan-3. And we do carry out preliminary orbit determination based on the NAINS data, navigation data available, GPS data available from the onboard, and it is showed that it is a perfect launch with very less dispersion in the achieved orbit. Then, after it is going into orbit, the important activity is attitude control, acquisition of attitude and the orbit. And orbit determination is a process. And orbit determination is carried out from using the ground station data, telemeter data, and a precise orbit was found out before going for earthbound maneuvers. Then it goes for earthbound maneuvers plan. As we can see that there were 5 earthbound maneuvers altogether, and which gives each maneuver will make, first it was in a GT orbit, then each maneuver will make a perigee thrusting using our thrusters in the spacecraft, and it will make the apogee larger and larger, imparting more delta V velocity to the spacecraft. At last, it has to go to a transfer lunar orbit. Okay. So for that, earthbound maneuvers, 5 earthbound maneuvers were there. All the 5 earthbound maneuvers were done properly, and after each earthbound maneuvers, there were a critical look into the aspects of the mission. All the health parameters were checked, all the telemeter data parameters were checked, and all the orbits were reanalyzed and calibrated. The calibration is done during calibration of the many systems, including navigation systems and thruster capabilities. Everything is done during the earthbound phase maneuvers, and some cameras payloads were operated, images were taken as a calibration process. Then it goes to transfer lunar trajectory, and basically it goes from earthbound orbit to the moon's orbit of 3.885 lakhs kilometers, and this TLI was done perfectly, and with enough velocity was imparted to this spacecraft so that it goes to a transfer lunar orbit. Then it goes for the moon-centric phase. In moon-centric phase, first important thing is lunar orbit insertion. So the delta V added to the spacecraft, which was taken to apogee of 3.85 lakhs, that has to be reduced to about 1.6 kilometer per second, so that it is captured by lunar orbit. It goes for a highly eccentric lunar orbit. It is captured there. Once it is captured there in the lunar orbit, it again goes for reducing the velocity, delta V reduction, so that it has to go for a final 150 kilometer by 150 kilometer circular orbit around the moon. So that is what done. So these are the moon-bound maneuvers. Again, you can see that there were 5 moon-bound maneuvers. And like I said earlier, after each of the maneuver, we were critically looking into all the data available. And if any corrections are required, that corrections being done, small corrections, mid-course corrections were done, so that it is actually goes for a geometry which is required for moon landing. Lander requires some particular geometry so that it will land in the designated place. Then it comes for, there is a propulsion module is there, and lander with the rover is there. It has to be separated from the propulsion module. Lander has to be separated. Then only lander will descend. So that again, that separation is one of the activity carried out in that phase 5. Then again, deboost phase. Actually, separation is happening by 150 kilometer by 150 kilometer lunar orbit. There again, separation happens, deboost happens. 2 deboost maneuvers are there, so that it will be taken into 150 kilometer by 30 kilometer perigee in the lunar orbit. Then it goes for a pre-landing phase. All the calibrations again done. All navigation parameters, bias, drips, everything has to be compensated. And we have to estimate the thrust levels, whatever we are getting from the propulsion systems. All those things are done, carried out. Based on that, the trajectory is finalized, fine-tuned. And also, for the landing, we have a throttleable engine is there, so that according to a profile, pre-designed profile, the engine will be throttling, and accordingly thrust will be generated, so that we can go for a soft landing. Then once it lands, there is a normal phase of rover comes out from the lander, and also other activities like rover movement, etc. were there. Now, as far as Chandrayaan-3 is concerned, now propulsion module is in lunar orbit, and lander and rover in the on moon. Now you can see the details of the all earthbound maneuvers here. And first satellite was injected into a elliptical orbit of 170, GT orbit of 170 kilometer by 36,491 kilometer. Then each phase, day by day, you can see that dates are available. June 14th, we have Earth parking orbit, it is there. EPO, it is there. From Earth parking orbit to first maneuver goes for 42,000 kilometer. Apogee is getting, always perigee will be nearly 200 kilometer. Apogee is getting added up, and it first bound maneuver goes to 42,000 kilometer. Then again there was a apogee correction maneuver. Apogee maneuver was there. Apogee correction maneuver was there. About the perigee is increased to 225 kilometer. Then finally it goes for, after last earthbound maneuver, it goes for it goes from 1,20,000 kilometer apogee to 3,85,000 kilometer in the LTA, trans-lunar injection, TLI. It goes. Then when it comes to lunar orbit, see, it is captured in a lunar orbit of 18,000 kilometer apogee and perigee of about 166 kilometer. And with that, again we have gone for reducing the velocity, so that it goes down to, after the 5th maneuver, lunar bound maneuver, it goes down to 153, about 150 kilometer circular orbit. Then we will go for the next 2 deboost maneuvers for preparing for landing. Their separation happens at 150 kilometer, lander and the propulsion module, orbiter in fact, or propulsion module is an orbiter. And then it goes for, separation happens at 124 by 160 kilometer, and it goes for first deboost. It reduced to 100 kilometer by 150 kilometer, and second deboost reduced the perigee to 30 kilometer. Then landing happened from 30 kilometer by 134 kilometer. The landing sequence is initiated. Now you see here, the lunar landing phase is a very important phase. There are 4 phases. First phase is rough braking phase. Second is attitude hold phase. We have to control the attitude. Third is fine braking phase, and last is the terminal descent phase. Okay. Vertical descent is happening there. Now in the rough braking phase itself, most of the velocities are killed. Velocity, whatever was there for the lander, it was killed in the rough braking phase itself. You can see that from 1.6 kilometer per second, 1.7 kilometer per second, it has come down to about 350 meter per second in the rough braking phase itself. Okay, and from there, it took about 11 seconds, 12 seconds, 12 minutes. It took about 12 minutes thrusting to do that. Then once it comes to and from 30 kilometer, it is coming down to about a 7.5 kilometer during the rough braking phase. From 7.5 kilometer at the end of the rough braking phase, the attitude hold is there. See, we have to control it. Control has to work in a closed loop thing. Now, control navigation guidance, NGC works in tandem with all the onboard systems. It works autonomously, and it's a closed loop system. And control is attitude hold was done in that phase. About 10 seconds attitude hold was there. And from there, their velocity reduction is not there. From there, it has to come to soft landing velocity requirement of 0 meter per second. So for that, it again take about 3 minutes time deboosting, fine braking phase. There, in fact, here the actual algorithm works brilliantly, so that guidance, command and control and navigation. Navigation, we have a system LIRAP. It's a laser-based gyro, and this system and accelerometer system package. This system perfectly worked and provided the necessary inputs for the control and guidance. So under the fine brake, at the end of the fine braking phase, it has come down to about 0 meter per second velocity. It is still, and it has already reached about 800 meters altitude. So from there, a vertical descent happens. Actually, the onboard lander imager, it will be imaging the land, specified land where to land it, the location. In fact, last 3 years, our CH2O, Chandrayaan-2 orbiter, it's a high resolution camera, onboard high resolution camera. It was imaging the landing site, and it made a lot of analysis, image processing, signal processing, and power spectral density analysis, spectral analysis, and generated a DEM, that is digital elevation model, for the landing site. So the lander is having onboard loaded DEM value, and whenever the image is coming, the lander will be checking, onboard it autonomously checking whether it is perfectly matching with even pixel level it is matching or not. Then it is deciding to go for landing. If in case if there is an anomaly found, or boulders are found, obstacles are found in the land, actually there is a provision for retargeting the landing also. But here what happened in Chandrayaan-3, it went perfectly and prime landing site. Actually our dispersion was very small for that, 500 meter by 500 meter, it has landed perfectly in that region. That is what happened. All the system parameters, all the navigation, all guidance, all control worked perfectly, and we got to the perfect landing. Now come to the ground segment support. Already our Victor has told that we had a global support for the ground systems, and India has got many ground systems which is supporting like for the launch phase and initial earthbound phases. All the ground stations from Bangalore, Lucknow, Port Blair, Mauritius, Biak, Brunei, these are all owned by ISRO. And we have a deep space network with 18-meter antenna and 32-meter antenna. These are all supported all our until the moon phase. Now, we have support from SSC, that Hawaii and San Diego, support was there real time, and we have support from ESA, Kuru, and Gunhili. Then, we had support from JPL, we had Madrid support, Canberra support, Goldstone support, but it was offline support, and we were using those data for orbit determination and analysis, everything. So, there is support from ESA, SSC, NASA, JPL, and our own deep space network we used for all these, including EBN and LBNs. Now you can see that rover path planning. Once rover is in the detached from, slided from the lander, it reaches the moon's land, and it started rover path planning. And rover path planning is done ground based, and there is a LI camera, that is lander imaging camera is there in the lander, and a rover is having rover imaging RI camera is there. They are imaging it imaging the place and finding out whether any obstacles are there, any hurdles are there, and those images are sent back to ground, and we are analyzing that, and the necessary command is given to rover for rover movements. So rover path planning is an algorithm with its optimal path, avoiding all the obstacles, boulders. Actually, you can see the slope in which a rover can move is less than 20 degree. So if it is more than 20 degree, we are not avoiding that path. Similarly, hazard boulder size more than 50 mm, more than 5 centimeter sized any object is there, any boulder is there, that we are avoiding that. And also shadows, because it is very important that we have to have necessary power in the system. So we have to avoid long shadows. We are doing a propagation. In case it's 12 days the rover was working on the moon, and 1 hour rover is stationed at a place, we have to propagate for the next few hours, so that next path planning has to be planned. For that, we are propagating it and see whether any shadow will be coming more on the rover, so that it can be stationed in a proper place, so that the power problem is not there. So that is done every day. It is done, and ultimately rover could move about 102 meters with the different 12 segments, 13 segments time. It has moved about more than 100 meters, and all the 14 days it was perfectly working on and it has done a lot of payload operations there. And regarding communication and power, we made sure that enough power is there for rover, and enough solar power is getting generated in the battery as well. So that is made sure. And communication-wise, rover communicate with the lander only, and lander only can communicate with the ground deep space networks as well as with the CH2 orbiter. Now you see the RF communication strategy-wise, we can see that important role played by the CH2 orbiter also. We used the CH2 orbiter for many purposes, including this communication, and also for landing site imaging by CH2 OHRC. Okay, here this CH3 propulsion module can communicate with the deep space networks, DSN, JPL is there, ESA is there, India, ISRO's IDSN is there, and also CH3 lander can communicate directly to deep space networks, and it can communicate with the CH2 orbiter as well. Similarly, CH2 orbiter is communicating with the deep space network, our 32-meter antenna as well as 18-meter antenna daily. And both the bands, frequency bands considering S-band and X-band are used. And for lander, rover can communicate only with the lander, and it is an X-band communication. Now I will request Dr. Gauri Shankar to proceed with the further science objectives and products. Thank you.
Good morning, all. It's my pleasure to present some of the initial science results, what we got in Chandrayaan-3, which is complementing the initial results, the mapping, global mapping results, what we got from the earlier orbiter, Chandrayaan-2 and 3. So the previous speakers talked about the technological aspects of this achievement. I will be presenting on the scientific aspects of it. So it's not only a technology demonstration mission to go into the moon, land there and rover there, but it had also a suite of instruments. These instruments are carefully chosen to complement the observation what we got earlier by our missions and also some of the missions of our partner agencies. These instruments which are there in the lander and also in the rover are the same as it was in Chandrayaan-2. You know, the Chandrayaan, we had the success of orbiter, but we narrowly missed in soft landing on the lunar surface, just a matter of few kilometers. These instruments, what I am going to present, and also the initial results, what I am going to say, in line with the scientific objectives, what we have put forth for this mission, both Chandrayaan-2 and Chandrayaan-3. Basically, we need to study what is the near plasma environment, what is the electron density, the ions concentration, how that will affect the radio communication when we go and establish our settlement. And it is also going to study the surface parameters, the physical, the chemical, elemental, mineralogical aspects. So to consider these two objectives, we had 5 instruments, 3 are on the lander and 2 are on the rover. I will get into the details, but in short I can say the lander had a Langmuir probe to study the ionosphere and also a seismometer to study the ground vibration and a thermal probe, basically a thermoelectric properties analyzer. The rover had 2 instruments, both are for finding the mineralogical and elemental composition of the lunar surface with in-situ analysis, whatever we have done earlier, or global mapping from 100-kilometer orbit, but the in-situ analysis, that too in near to the South Pole region, that is the element. So it had 2 spectrometers, which are operating with 2 concepts, like laser beam induced and also the alpha particle X-ray spectrophotometer. One is good for elements of lower atomic number, another is for higher atomic number. Another interesting instrument also we had, which is not having such relevance for lunar surface, but the propulsion module, which has helped us in taking the lander module from launch phase, the injection phase, to the landing phase, to the lunar orbiting phase, has had one interesting instrument, which is a simple instrument, which is of futuristic in nature. It had a spectrophotometer, which can take the reflectance in near infrared region with just simply 6 pixels, how a habitable planet behaves when the sun is heating it. Like sunlit portion in the near infrared region, it's measured by this particular instrument. Basically, this is for a future purpose, like when we go for finding some exoplanets in other solar system, we will be in a position to compare with these results and try to take some decision. Another interesting instrument which I have not listed here is a small passive instrument from NASA, basically a laser retroreflector array. It is going to be a permanent marker on the lunar surface, that too in lunar South Pole, for current and also the future lunar missions. It can help in locating themselves. The future missions can help in locating themselves by sending just a laser pulse and getting it reflected, because it doesn't emit anything, it just reflects whatever it falls on this. So with this brief background, I am going to say few initial results what we got from the lunar science point of view. Basically, the 5 instruments, Langmuir probe, thermoelectric sensor, the seismometer, the spectrophotometer, which are operating with 2 principles in rover. The first one is the Chandra's surface thermo-physical experiment. Basically, it was meant for studying the thermal profile of the lunar surface from top to around 10 centimeter below the surface. It had 10 thermal sensors, which are not equally distributed. Few are, closely placed in the top and, with the distance at the bottom. It also had a control penetration mechanism, so that you can analyze the compactness also, how the surface is compacted, what could be the physical structure of the lunar surface. And it also had a heating source, so that the thermal conductivity, the heating source will go to the bottom at 10 centimeter. From there, it sends the heat, how this is getting transmitted to other region to the surface. So the thermal conductivity of the lunar surface also was analyzed using this. The initial interesting results, what we have found is shown in the first graph. You can see a thermal gradient of around 60 degrees Celsius from the top of the soil to the 10 centimeter below the soil. And another interesting feature is seen in the other graph, which is in the right side, where the gradient, which is of 60 degrees on the top of the surface on the first day of the lunar day, is slowly coming down. It is narrowing down on the end of the lunar surface, basically indicating the poor thermal conductivity what the top 10 centimeter regolith has. I can tell you this is the first detector or direct measurement what we have seen, the humanity has seen on the lunar surface, that too in the near lunar south pole. The results from this instrument certainly can give valid vital input for us to choose the material when we are going to establish some infrastructure in the lunar surface for different purposes which the entire global lunar community is speaking about. The second instrument I am going to talk, which is on the rover. Basically, it's a spectrometer. It's operating in a principle of inducing or sending a laser pulse, ablating the surface and measuring the emission which is coming from, which are characteristic to the element which are present on the lunar surface. Maybe in a simple terms, you can say emitted plume as a result of surface ablation by pulsar laser is measured by this instrument. You can see the peaks which are characteristic to different elements, and to our surprise, which was not found on the orbital analysis, presence of sulfur, that too in abundance, is identified this particular instrument, apart from identifying some of the other peaks like iron, aluminum, titanium, chromium, and calcium. Another instrument of similar nature, which is APXS, I'm sorry, can somebody help in moving to the next slide? Yeah, this also is a spectrometer which works in a different principle. It has its own radioactive source. It emits alpha and X-ray particles on the surface, and the elements which are present react to this particular X-ray, and the characteristic X-ray lines corresponding to the element present is measured by this particular spectrometer. Again, this particular instrument has helped us in discovering the presence of minor elements including sulfur, as was done by the previous LIPS instrument, and also some of the expected major elements like aluminum, silicon, calcium, and iron. And I can tell you that the finding from these two instruments certainly can have significance to infer on the mineralogical composition of the lunar surface, and also, that too in the near south pole, where more activity is going to happen from humanity in the future. One instrument, a Langmuir probe, which is on the lander, basically to study the plasma, near plasma ionosphere, basically to study the electron density and ion density, is mounted on the lander. It is so characteristically placed, which is the lander is about 1.5 meter above the surface, and the probe has gone 1 meter from the lander surface so that there is no interference from the lander body. And one interesting picture, which is in the bottom of the slide, taken by the lander camera, which shows the shadow of this probe on the lunar surface. It has a 5 centimeter metallic spherical probe, and it measures the return current by applying a sweeping bias potential, which ranges from -12 to +12 volts. The sensitivity of this instrument is it can measure the return current as low as a picoampere, that to every millisecond. The initial results reported low plasma densities in the lunar surface, maybe tens of hundreds of electron per cubic centimeter, or we can say 5 to 30 million electrons per cubic meter, which is relatively sparse compared to the Earth atmosphere. And this particular study or the results can help us in finalizing the frequency what we need to use for when we go for doing some radio communication on the lunar surface. Suppose if you have a settlement, how you can communicate, which frequency you can use, higher frequency or a lower frequency. So certainly this particular result will help in that phenomena. Yeah, another instrument which is on the surface of the lunar South Pole, but it's mounted on the lander. It is dropped basically to see the vibrations on the ground. These vibrations could be either natural or artificial, like it could be moonquakes or asteroid impact or any artificial event, including the rover movement or drilling activity. All those things can be measured, and it's a MEMS-based instrument with a cluster of 6 high-sensitive accelerometer, and the external vibration leads to a deflection in the spring, and the spring direction changes, resulting in a change of capacitance, and which is converted into a voltage, and that is measured by this instrument. Through the graphs we captured in the left side, there are 2 graphs, blue graph and the red. The blue graph indicates the artificial vibration which has been created by the rover when it was in operation, when it was moving from lander to explore the surface. And the bottom one is indicating a 4-second event which is not conclusively concluded, means it indicates that it could be a natural phenomena, could be a meteoroid impact or a moonquake, or all those analyses are going on. So during this one lunar day of operation, we had recorded 57 events of rover movement, which is shown in the pie chart, and more than 100 events of instrument operation, both the chaste and the seismic activity, the other one, the instruments which are on the rover, and more than 50 unidentified events. This particular segment will be of interest to the scientific community. The results from this Chandrayaan-3, the in-situ analysis, will not be analyzed in isolation. It will certainly, once we will be doing individual analysis also, bringing out some scientific results, but also it will be analyzed in correlation or in relation with the results what we got in Chandrayaan-2 orbiter. So I'm trying to show here the connections between the results what we got in Chandrayaan-2 and the results what we are going to get in Chandrayaan-3. Basically, you can see the localized in-situ measurements what we got, what we are going to get in Chandrayaan-3 is going to complement the Chandrayaan-2 goals. For example, I can tell the radio occultation experiment what we did in Chandrayaan-2 can complement the measurement of the near surface plasma or which is analyzed by our Langmuir probe in Chandrayaan-3. The thermophysical properties analyzed by chaste in Chandrayaan-3 can help in constraining the model which we are using it for analyzing the surface hydration and surface roughness in Chandrayaan-2 using the 2 instruments. Just give an example. So this is not science, but again, 1 or 2 slides I would like to say, which are all the other things which we have done which exceeded the mission objective. just before end of the lunar day, an unplanned activity was carried out, which has high significance for the future missions. By retracting the primary ramp, which deployed the rover, and also the three instruments, Chaste, Ramba, and ILSA, the two engines what we used for landing were fired for just 1 second. This has helped the lander to go up around some 40 centimeter above and then land some 30 to 40 centimeter from the initial phase. This is of significance in two angles. One is we could do the measurements what the lander instruments did in the first place, it could be repeated on the second place. We did. It is another level of, checking whether the consistency of these measurements, number one. And number two, how we can reignite the engines so that if there is any future sample return mission or there we can try to use it. So that significance, it has helped. And this is the fantastic image. What we got is a classic image. What we got from the OHRC, we call it as Orbiter High Resolution Camera mounted on Chandrayaan-2. It is the highest resolution imager as on today on the lunar orbit, and it has taken the lander, which you can see in the center of this image, a white pearl-like thing with its shadow. So you are seeing the shadow of the lander among the shadow which are created by the craters. It's worth mentioning here that this particular instrument, which is of in Chandrayaan-2, the Orbit High Resolution instrument, or the data is given to other partner agencies to help them in finalizing some of the landing sites for their future missions. This is my last slide. Sorry for taking extra time. I would like to say that this mission is not Indian national endeavor alone. It had a lot of ingredients to say it's an international cooperative mission. We mentioned there is a LRA from NASA. Apart from that, interestingly, they said there are some network of ground stations what we used, the countries we have represented here. And we also had support from 100+ companies, both from India and abroad, for through purchase procedure or sourcing the components for this. Certainly, the data from this mission will help in bringing more collaboration nationally and internationally. And we close this presentation by the picture of lander majestically standing on the lunar surface, taken by the navigation camera, which is mounted on the rover from a distance of 30 meters. So thank you so much for your patience.
Thank you. Now, considering the time limitation, we'll take maybe 1 or 2 questions. First one is on the navigation algorithms. So what I have to tell here is we have used more than 6-7 measurements, including velocity measurements, altimeter, as well as acceleration, and also camera for the navigation and guidance. So the second question is regarding why the Vikram and the Pragyan did not wake up. I request Anurup to.
Yeah, this is a question that we have been facing throughout. See, the mission was designed to last a lunar day, and then we allow it to sleep, and then people got so attached to the mission that we are all facing questions like, hey, why didn't it wake up? Why did it wake up? So the emotional attachment, yes, we are encouraged by the emotional attachment that is being shown to the mission, but the mission has completed its objectives. So whatever we get beyond is a bonus and will add to science in whatever way it is possible. But the reasons could be anything, because considering the very cold temperatures of around 200 degrees Celsius, plunging down at a fast rate during the lunar night, the mission is not designed to do that. So, but still, that is anyway, it has finished its objectives.
Thank you. What is the fuel remaining in the booster module, and what we are going to, how it will be safely disposed?
In fact, for any mission, any spacecraft mission, including Earth orbit or interplanetary or lunar orbit, enough fuel will be loaded so that to take care of any dispersion levels, known or unknown, injecting orbital parameters, dispersion, etc. So that way, this our propulsion module also was having a lot of fuel stored in it, and but luckily because of the trajectory, the perfect planning and the perfect thrusting, everything, the lot of fuel left now as of now. I don't want to tell the actual number here, but as such, this fuel, we are planning, our high-level committee will be going through it, and now the propulsion module is in 150 kilometer by 150 kilometer orbit with some fuel there. That anyway has to be decided later.
So thank you. And I think the advice to other countries will be design, test, simulate, go on testing, do the simulations so that there may not be much of an issue during the flight. And one more question is again to Anil only, the launch shift of 4 seconds to avoid collision. Want to answer that?
What is question?
Launch shift of 4 seconds was mentioned to avoid collision.
Yes. Okay. See, this is a practice. It is a mandatory practice for not only for ISRO, all the space launch vehicles. That is, before launch, the liftoff should be cleared. So it has to be analyzed against the, now you know that debris, number of space objects in the orbit, especially Earth orbit, is so high, and even NASA, US Space Com is tracking more than 30,000, cataloging more than 30,000 objects with size more than 10 centimeter. See, this always gives problem. Close approach criticalities are there with the ascent phase of the launch vehicle as well as the initial orbital phase. So this collision avoidance analysis is a mandatory thing for Indian launch vehicle for clearing the liftoff. And for this LVM-3 launch that particular day, the liftoff, nominal liftoff time when we analyzed, we found that during its first orbital phase of Chandrayaan-3, many objects, actually including operational objects, are coming close less than 1 kilometer to that orbital phase. So we have shifted it by 4 seconds to account for all dispersions, everything, and inaccuracies in the orbits, etc., orbital observations, etc. So we shifted by 4 seconds to avoid a close approach by other space objects.
So thank you ISC for giving us, thank you once again for giving us this opportunity to present Chandrayaan-3 as the late breaking news. Thank you.
Thank you.